Hey everyone, and welcome. We tend to think of computers as these miracle machines, right? Capable of solving almost any problem if we just throw enough power at them. But what if I told you there are problems out there that are fundamentally impossible to solve, no matter how much time or processing power we ever have?
And that's the big question we're diving into today. Now, I'm not talking about problems that are just really, really hard or take a super long time to figure out. No, we're talking about problems that have been mathematically proven to be unsolvable by any computer, by any algorithm, ever. So how is that even possible? Well, to get our heads around it, we first need to understand what it even means for a problem to be solvable.
It all comes down to this key idea from computer science: decidability. See, a problem is decidable if we can write a program that's guaranteed to solve it. It will always stop and give you a correct yes or no answer. But then you have the undecidable problems. These are the real mysteries, where it's been proven that no such perfect, all-knowing program can ever be created.
So to investigate these strange limits of logic, we're going to need the right tool for the job. And in the world of theoretical computer science, our ultimate detective is a concept called the Turing machine.
Now, a Turing machine isn't some physical gadget you can buy. It's a mathematical model, an idea. Think of it as the most powerful, stripped-down, theoretical computer we can possibly imagine. The basic idea is, if a Turing machine can't solve a problem, then no computer, anywhere, ever can solve it either. And what's so cool is just how simple this powerful idea really is. You've got an infinite tape, kind of like a never-ending scroll of paper. You've got a little head that can read what's on the tape, write something new, and move left or right. And finally, you have a set of simple rules to follow. That's it. Everything we think of as computation can be boiled down to this elegant model. Okay, so we've got our detective, the Turing machine. Now let's go after the most famous cold case in all of computer science, the halting problem. On the surface, the problem sounds pretty straightforward. Can we create one single master program that can look at any other program and its input and tell us with 100% certainty if that program will eventually finish its job, what we call halting, or if it's going to get stuck in an infinite loop and just run forever? So let's just pretend for a minute that we could build this. We'd have this amazing halting machine. You'd feed it any program you want along with its input, and it would just spit out a clear answer. Yep, it'll halt, or nope, it's going to loop forever. Seems useful, right? Okay, now this is where the logic gets really, really clever. To prove our hypothetical machine is impossible, we're going to build a new, kind of mischievous program that uses it. Let's call this new program the inverter. All the inverter does is take the halting machine's answer and do the exact opposite. So if the halting machine looks at a program and says, yes, this will halt, our inverter intentionally throws itself into an infinite loop. And if the halting machine says, no, this will loop forever, the inverter just immediately halts.
Now for the brilliant, brain-breaking twist. What happens when we ask the halting machine to analyze our weird, paradoxical inverter, and we give the inverter itself as the input? And right here, the entire idea just collapses into a logical paradox. Just think it through. If our machine predicts that the inverter will halt, well, the inverter's own rules say it must then loop forever. But if the machine predicts that the inverter will loop forever, its rules say it must halt immediately. It's an impossible situation. And this contradiction leaves us with only one possible conclusion. Our first assumption was wrong. A perfect, all-knowing halting machine just cannot exist.
Now, this proof isn't just a one-off party trick. The halting problem was like the first domino to fall. It revealed that there's a whole class of problems that are fundamentally unsolvable. Let's check out another one that looks deceptively simple.
So picture this. It's a kind of puzzle called the post-correspondence problem, or PCP for short. Imagine you have a set of dominoes, but instead of dots, they have strings of characters. For example, say you have 3 dominoes. The first has 10 on top and 101 on the bottom. The second has 011 on top and 11 on the bottom. And the third has 101 on top and 011 on the bottom. The goal of the game is to find a sequence of these dominoes. You can reuse them as much as you want, so that the long string you get from reading all the top parts is exactly the same as the string you get from reading all the bottom parts. Seems like a fun little puzzle, right? You could probably sit down and find a solution for that specific set of 3 dominoes if you tried long enough. But here's the kicker. It has been proven that it's impossible to write a single computer program that can look at any set of these dominoes you could possibly dream up and tell you for sure whether a solution exists or not. Just like the halting problem, it's undecidable.
So, okay, we've got problems that are flat out impossible. But what about the ones that are technically solvable but just insanely hard? Well, this brings us to one of the biggest, most famous mysteries in all of mathematics and computer science: P versus NP. So, this slide breaks down two really important classes of problems. First, you have P problems. You can think of these as the easy ones, meaning a computer can find a solution for them efficiently in what's called polynomial time. Things like sorting a list of numbers. But then, you have NP problems. For these, we don't necessarily know a fast way to find a solution, but if someone just hands you a potential answer, it's very, very fast to check if they're right. Think of a massive Sudoku puzzle. Super hard to solve, but if I give you a completed grid, you can check it in a minute. And that leads us to the million-dollar question. And I mean that literally. There's a $1 million prize from the Clay Mathematics Institute for whoever can prove it. The question is, does P equal NP? In other words, for every problem where a solution is easy to check, is there also an easy way to find that solution in the first place? Right now, nobody knows.
This diagram kind of shows how most experts in the field think these classes are related. The general belief is that P is a smaller circle inside the much bigger circle of NP. This would mean that there really are problems out there that are genuinely hard to solve, even if their answers are easy to verify. But as of today, it's all just a very, very educated guess. No one has been able to prove it. All right, so undecidable problems, the P versus NP mystery. This all feels pretty abstract, right? Why do we actually care about any of this? What does it mean for us here in the real world?
Well, it turns out this isn't just theoretical navel-gazing. These limits have very real, very practical consequences that directly affect the technology we use every single day, especially when it comes to keeping our computers safe. Let's take virus detection, for example. We'd all love a perfect antivirus program, one that could spot every single possible virus without fail. But creating one is impossible. And why? Because fundamentally, the virus detection problem is just the halting problem in disguise. A super clever virus could be designed to only do its damage if the antivirus program analyzing it finishes its scan. So to be perfect, the antivirus would have to predict whether the virus program will halt, and we already proved that's impossible. So if there's one thing to take away from all this, it's that computation isn't magic. There are hard, fundamental limits baked right into the laws of logic itself. These aren't just engineering challenges that we can overcome with faster chips or cleverer programming. They are permanent boundaries of what is and what is not possible to compute. And that leaves us with one last pretty big thought to chew on. If the very foundation of computation has these built-in, unsolvable problems, what does that tell us about the ultimate potential and maybe the ultimate limits of artificial intelligence? Something to think about. Thanks so much for tuning in.